So in this video we're going to look at the mean value theorem for derivatives. As I have written here on the right, the mean value theorem states that f prime of c will equal f of b minus f of a over b minus a. Let me flush that out a little more. The theorem is first prefaced by saying the function must be continuous on the closed interval from a to b and differentiable on the open interval, which is pretty much meaning it's a nice smooth curve that doesn't have any discontinuities. It's differentiable on all places. It has no sharp points and whatnot. So if we understand continuity, we can conclude, okay, our curve is continuous, then we can use the mean value theorem. Now, the mean value theorem is saying there must be some number c such that f prime of c will equal f of b minus f of a over b minus a. So let's think about what that means on the graph. I have here on the left the graph of y equals x squared. If I have a point on this graph, and I'll call that point a and f of a, and we know that f of a will be a squared. And I have another point b and f of b, which will be b squared. If I draw a line connecting these 2 points, it's a secant line that's intersecting the curve twice. The slope of the secant line is going to be y2 minus y1 over x2 minus x1. Well, that's what this is saying on the right side of our mean value theorem. F of b minus f of a over b minus a, that's y2 minus y1 over x2 minus x1. So with that in mind, what we're really looking at with this curve is we're saying that at any 2 points we draw a secant line through it. There must be some point within that interval, some point we call c, such that the derivative evaluated at that point will equal the slope of the secant line. Well, what is the derivative? It's the slope of the tangent line. So the idea behind the mean value theorem is that if a curve is continuous and differentiable, then we can draw a secant line between 2 points on the curve, and within that interval there must be some point that we can draw a tangent line that would be parallel to the secant line. So just a basic example here with y equals x squared. We would say we'll work with the interval from 2 to 4, and we want to know what is the value of c. Well, the derivative of x squared is 2x. So f prime of x equals 2x. And that's going to equal f of b. Well, in this case, b is 4. F of b is 4 squared, so that's 16. Minus f of a. A in this case is 2. 2 squared is 4. Over b minus a. And when we simplify that, that's 12 over 2 which is simply 6. And the mean value theorem is saying there's some number c such that the tangent line will have the same slope as the secant line. Well, the tangent line slope is 2x, and that's equal to the slope of the secant line. Well, x is that value c, or we could plug a c in there if we want. It's just an arbitrary variable. If we solve the equation, we divide by 2, we get x is equal to 3. And what that is saying is at x equals 3, the tangent line will be parallel to a secant line that's going through the points 2 and 4. And that makes sense if you think about it, since y equals x squared is symmetric. It's nice and smooth. It would make sense for our tangent line to be going through the middle, exactly in the middle between the 2 outer boundaries. And that won't always be the case, but as a general rule, your mean value theorem is going to land your number c somewhere around the middle of the interval if it's a pretty smooth, somewhat symmetric curve. And the idea behind it is simply the tangent line will be parallel to the secant line, assuming the curve is continuous. And we use this in a lot of proofs and other things farther along in calculus. It's a very powerful theorem as we move ahead. And I think it's important just to understand the intuition behind it. The mechanics are fairly simple. If you can take a derivative, you can solve an equation. It's quite simple. But your focus needs to be, do you understand that you're getting a tangent line parallel to a secant line, because as you go along that can be a very useful tool when you're proving a lot of other things.